good to see this many people in this room. I appreciate taking the time to join this session today. My name is Petri Wilhelmsen. I'm currently working in a company called Dolittle, which is basically a startup here in Oslo. I'm currently working around the digital twins, visualization, graphics, and that kind of stuff. Mostly within like using 3D technologies such as Unity, Unreal, or even custom engines to kind of visualize data or even create models that replicate real-world assets. And that's what I'm here today to talk about. I want to talk to you guys about the digital twins and how you can kind of understand how they work, and even, maybe even go home and see, test how we can create that. So today's talking points, I want to start by just telling you kind of what the digital twin is, the basics around that. How do we in Dolittle define digital twins? How do we work with them? I know that there's probably a couple of you guys in the audience that's been working with digital twins or even rendering. But this is kind of our take on this. I know that there's a lot of different definitions. So I want to talk a little bit around that. And then I'm going to move into just letting you guys know how kind of I ended up working with these kind of technologies right now. And then I'm going to move into how you can create digital twins yourself. This is going to be a beginner's talk, so I want to go into the basics of Unity and how that works and how we can add some custom scripts and get connected with the internet. Hands up, I just want to see how many of you guys have been using Unity before. So there's quite a lot of experience here. That's awesome. Okay, yeah, I hope that you can take the existing skills. I know that some of this part might be a little bit basic, but I hope that there's something new here as well for you guys. I tried to make it that way. And then for all of you who haven't touched Unity before, I want to just kind of show how that works. Then thirdly, I want to touch more into a real-world digital twin that's actually connected to the cloud. It's using some machine learning and that kind of cool stuff. And then in the end, I want to just move a little bit into kind of modern interaction models and how you can interact with software in a little bit of different way than what we're used to up until now. So if we take a step back in time, models has always been something that we've been making. If we want to build a building, if we want to create some architecture, if we want to model a car, or even create a car, we like to sculpture the car. We want to see how it actually looks in real size. And then we like to add some physics to it, like will it stick to the road? In this example, on the screenshot here, there's a model of the Mercury space capsule that was made by NASA in kind of the 50s. This is in a wind tunnel. And this is a real replica where they actually tried to see if this one could kind of sustain the forces during re-entry. And they used a wind tunnel to do that. They want to see how kind of the wind affects the body of it and see if nothing falls off, which would be very unfortunate for the poor guy inside. So when it comes to 3D models, we have a lot of different ways of looking at them. What you see here is just a simple 3D model of an engine. It's based on a real-world asset. So if I kind of move around here, you can see that I can look at it from different angles. There's a lot of details to it. It even has all these kind of parts that fits together. This is just a 3D model, but since we're on a computer software, and I'm currently running on Alienware, but one of the cool things about kind of these years we're in right now is that the hardware is getting much stronger. You can run this on kind of old enough laptops. You can get cheap graphics card. There's a lot of availability of hardware currently, so you can easily start rendering stuff like this. 3D model is just one aspect, but if I want to go ahead and take this a little bit further, I can actually add some simulation to this. One of the ways of adding simulation on a jet engine is, of course, to ignite it. The way this engine works is that it's attached to an airplane, let's say a Boeing 737 or something like that. They're currently pushing off from the terminal, and they're firing up the engine. The engine is pre-configured to a target air temperature of 21 degrees, and then N1, which is the inner spool, and then N2 is the inner spool, and then N1 is the air intake. they spool it up to a pre-configured setting based on the configuration of the airplane, weight, and all this kind of stuff. The engine is now up and running. It doesn't produce any thrust. So what they do next is to add a little bit of thrust. They go to the runway, and then when they're on the runway, they hit something called toga, which is take off and go around. Once they do this, this will then spool up and start applying thrust to the airplane. And once the pilot releases the brakes, it's going to start rolling and eventually take off at the correct speed. There's a lot of configurations involved here, including like noise reduction. They don't want to have full thrust if the airport is like above a city. There's some acceleration fields and stuff like that. This is purely a simulation, but it's a model of a real-world asset. Another example is if we go out to the ocean, we're having a different model. This is a model of a windmill, or I think it's like a wind turbine. This one is actually connected to a sensor that sends me data. So this model is just constantly receiving data from a real-world sensor. This is something that we like to call a device shadow. It's within kind of the digital twin family. We're trying to visualize a model that's replicating the real world. But the cool thing here is that I can actually now go ahead and start overriding these values from the sensors. For example, I'm currently receiving a wind direction from somewhere out in the ocean and a wind speed, right? It's changing a little bit. There's some gusts involved and stuff like that. But what if I override this and start changing the wind direction? You can see that the relative wind speed is getting slower, it's being less efficient. By doing this, by applying simulations to kind of a living model, you can start understanding how this system actually works, and then you can start playing around with it to see how it affects your real assets. And this is to test kind of your algorithms on making this one turn against the wind better, which they actually do, of course. This is just an example. And so on. This kind of leads us into how we define digital twin, and this is kind of how we do in Dolittle as well. We tend to think of these assets as a replica of a real world asset, which is a living asset because it receives data from sensors. It's an actual copy of something that exists. The other thing is that by applying machine learning, by reading this data, by analyzing this data, I can start to make the model learn about its environments. I can apply different things that maybe I'm not able to think about, but the environment kind of produce on it. The last thing that I previously mentioned was the ability to start experimenting with models. By using simulations, you can now start experimenting and see how it's being affected by the real world. There's a couple of input models to these different windmills. So let's say we have a fleet of windmills. The first input model is, of course, by zone sensors. It's reading data from the sensor itself. The second one is that since I'm having a fleet of windmills, I'm now able to gather data, like if all of they communicate data into the cloud, I can then start processing this data. I can start training machine learning models to be able to predict everything that might happen around it. This is what we kind of like to say as a fleet input model. It applies kind of surrounding best practices around the real world around you. And then lastly, the simulations, as I mentioned earlier, and the human knowledge. What do I know about this system? All of these are also inputs to your digital twin. So this is kind of how I would, I'm not going to go too deep into this, but I want to just kind of make sure that everyone in this room understand what we think about when we're talking about digital twins, at least from my perspective. My background on how I got into kind of the digital twin thing was that I've always been a graphics programmer. I like to make stuff in graphics in real time, especially. Everything from going to the gathering in Hamar every Easter for a lot of years. competing in the demo scene competitions, trying to get that little, part of the money from the prizes there, together with the team. I started on a C64 that my dad gave me when I was young. I'm not like C64 age. I was born a little bit too late for that, but we still had one, and it was a lot of fun. I spent the last 8 years in Microsoft before joining Dolittle, where the last 3 years was in the headquarters over in Redmond. In Redmond, I worked quite a lot with HoloLens, mixed reality, virtual reality, and how you can apply graphics. I had a couple of partners around the world that I kind of worked with, but in addition, we also made stuff for our conferences, like the Build, Keynote, and a couple of the other ones around the globe, where I made demos. I didn't go on stage myself. We were just sitting behind the stage doing cool stuff, and then someone else presented the demos. But if we go away from kind of the graphics aspects, I've always been super interested in simulations. This is kind of a replica of a Boeing 737. But when I was young, I had a kind of a fireproof flight suit, and I even had a helmet with a replica of a real joystick, and I hooked it up with my computer. And we were flying around with some guys, with my old friends over there in jet fighters. It was super fun. Then I found this guy. It's an officially licensed Boeing simulator that you can even just download on your PC and start playing around with. I spent around 6 months trying to learn all this. This is a really good simulation. It has all the electronics in there, voltage, everything like that. And the cool thing about this is that you can just kind of see how the real captains were doing stuff, and you can have the real checklist that the pilots had, and you can start flying. So this made me actually really curious. I wanted to kind of understand how all of this actually works in space. So I'm no longer limited by the atmosphere and having some air and air drag. I can now go ahead and get out of that, out of the surroundings of our safe haven here in this universe, and explore what's out there. That's pretty cool, but I wanted to understand the physics, and I wanted to understand kind of how the orbital mechanics works, and how all these kind of technologies that we had like in the early rockets from the 50s and 60s and this early 70s, how all this actually made us, in the end, land on the moon. So I was quite fascinated by that, so I spent a lot of time kind of Googling how and about trying to find kind of a good simulator to do this. But unfortunately, I wasn't able to find one. So I did the huge decision of actually go ahead and create one myself. And this is actually the cockpit of Apollo. So I'm currently sitting inside of Apollo. This is my own custom physics engine, but it's rendering inside of Unity. If we take a closer look at what I actually have here, I can now go ahead and start applying, power to a couple of systems. We need some power, so I'm going to just do a couple of these things. You can see that things are changing. There's actually electricity going on inside of this. So I'm kind of having just some classes that kind of simulates the electricity flow, liquid dynamics, and stuff like that. So if I take a closer look at what's actually going on here, I'm trying to get into orbit around Earth. It's kind of in the wrong position right now because I just fired it up before the talk. But if I go back into the simulator, I can separate myself from the launch vehicle. So if you go outside again, you can see that it's now opening up. And then I can go ahead and apply some attitude controls, some rotational controls, translation. And if I now start looking out of the window, and I hit pitch on the joystick, it will actually start rotating down. I can see Earth in front of me, and eventually, of course, the launch vehicle itself. So I'm just going to quickly navigate here. There we go. And then I could perform a docking maneuver on the lunar module. I can translate a little bit back. But the thing here is that everything here is simulated. So if I move closer to this guy, and I start applying thrusters, you can see that it's actually using these thrusters, and it's all visualized quite beautifully, and the way that it actually looked like in the real world. So, just going to go back to the slide. Actually, I'm just going to close this one down as well, just to free up some memory. So this is kind of how I ended up working in Dolittle. So I was doing all this stuff when I was in the States. I was doing these things with the customers, and I decided that I actually want to move ahead and go this direction. And I joined Dolittle back in February this year. So after that, I've been working on this full time. Yes. So with that, I wanted to just kind of launch Unity, and I'm going to tell you kind of the basics of how Unity works. We're not going to be writing too much code, but I'm going to have a couple of lines that I want to show you. And the goal of this little session here is to make a small desert simulator. So I want to just go into Unity. I'm going to grab some terrains. I'm going to add some stuff and add some physics to it and start playing around, just so you can see how easy it actually is. The goal is not that you maybe should be able to go home and do exactly the same thing. Some of you will, probably. But the goal is that I'm going to replicate all of this in step-by-step tutorials that I will share afterwards, so you can still follow along. So I'm launching Unity 2017 right now. I know 2018 is out there, but this is what I had installed currently. And I'm going to create a new project here. Let's call it NDC Desert Sim. Perfect. 2018. That's you also have every simulator has like a year behind them, so we got to have that too. So now I'm going to go ahead and launch Unity. What Unity does now, it's just to create a folder on your local hard drive that contains kind of the basic template project. This is like just a kind of setup properties, settings that are initially there, and then it's going to add a couple of small things. So once this is done with this, we have Unity loaded, hopefully soon. There we go. And this should now be a blank environment. What you can see in front of me is just the basic user interface of Unity. We have a scene view here. This is kind of how the scene is currently looking from an editor perspective. This is where you drag and drop and do stuff. Then you have a game view, which is kind of the eyes of the camera. So if you hit play and you start playing your game, you can see it through this perspective. The other thing I have is a scene hierarchy. And I know that the font there might be a little bit small, so I'm just going to read out loud everything that I'm kind of pointing at, just to make sure that everyone all the way back there can see what I'm doing. The scene hierarchy is where all the objects of my simulator is. Unity works in a component-based model, which means that you add a basic game object. It's called game object. You can think of this as an object class. And then you take this game object and you customize it with components. And there's a hierarchy in here, so you can make like one game object a child of another one, and then you can kind of build your own models and logic based on that. So currently, in the scene, I have a main camera and a directional light. This is what's default being added to a Unity scene. The main camera is consisting of kind of a name. You can think of this as kind of its variable name, but things can have the same name as well. And then it has a transform object. Every single game object in Unity has a transform object, with some exceptions, of course. You can think of this as an atom. It's like the basic building block of your game. And then it has a camera component to it, which defines this game object to become a camera. It contains logic. It comes with Unity that it says that this is a camera. And the same with directional light. So this is the light. It has the position, and then it has the light component to it that defines that, hey, I'm a light. I'm currently a directional light. You can set different kinds of light that's been built in with Unity. And then you have a color, you can have intensity, and so on. So you can kind of set up the lighting the way you want. Usually you want to have more than one light source because there's a lot of things going on, especially indoors, that make things realistic. But today we're going to be outdoors, so I'm going to need a sun. So let's add a sun. There we go. And then secondly, in a desert, we need to have the desert itself, right? So I'm going to go ahead and add the terrain here. So I'm going to right-click. I'm going to select a 3D object, and then select the terrain object. This is now adding another game object into my scene, which contains a terrain component and a terrain collider, so I can start colliding with this terrain using the Unity's built-in physics engine. So if you take a look at this from this perspective, you can see that I have a huge terrain here. The problem with this terrain is that I like to work with Origo. I want 0, 0, 0 to be kind of the center of the world. The main reason for this is that in simulation, especially in space simulation, you're working with huge environments. And Unity is unfortunately only floating point based. So if you want to have precise calculations on your distance, you want to try to be as close to Origo as possible to have as much as floating decimals as possible. So that's my reason, but I know there's a lot of people who don't like that. But I'm going to just move this back into, let's see, 250. I think that this is what I did during practice. There we go. So if I go ahead now and right-click and create a new sphere, and I want to position this in Origo of my scene, it should be right in the middle. There we go. So I'm going to leave the sphere there because I'm going to use it as a reference later. But the first thing I want to do is to actually add some sand texture. So I'm just going to do it in a very cheap way. I'm going to fire up Google. I'm going to search for filter forge, desert maybe. Let's try that. Pictures. Yeah, this one seems nice. Filter Forge is actually a pretty cool tool that you can use. There's a license to it. I both like a lifetime license. But it has a lot of cool textures that you can easily just muck up stuff with and start getting creative. And then once you're kind of getting closer to an end project, you can start creating your own textures or talk with a kind of an artist that can create them for you. So I'm going to right-click here. And then I'm going to save this image. And let's see, what was the name of this? It was NDC Desert Sim. I'm going into Assets. And I'm going to create a new folder called Textures. I'm going to save this. Actually, I have a better idea. I'm just doing a little bit here on the flow. I'm going to save the diffuse map instead, and something called a normal map. I'm going to tell you what these are in a second. So I'm going to save this image as well. There we go. Right. I now have my sand textures. It's automatically detected by Unity and applied into my scene. So if I go into my textures folder here, I can remove this guy. I now have the diffuse map. The diffuse map, or albedo map, is kind of the color of the sand with no light applied to it. It's kind of no shadows, there's no dents and bumps in it, it's just a pure color. So the normal map, which is something I need to set as a normal map in the Unity settings. So I just click here, go into Inspect and View, and select normal map, and I hit apply. Unity will then process it and consider this as a normal map. What a normal map really is that it contains this color map is pixels, but each of these pixels are actually a vector. You can see that this has kind of this blue, pink, violetish color to it. It's an RGB color, which is 3 floating points, which is also the same as a vector. So you don't have to look at this as an image that you would like to, look at and think is nice. Look at this as kind of the bumpiness of the surface, and it's in terms of just vectors. So what I'm going to do now is to go into my terrain, and I'm going to go to the painting brush here, and I want to apply this texture. The first texture you apply to a terrain will be automatically applied to the entire thing. So I can go and hit Edit Textures, Add Texture, and in this view, I need to set the color and the normal map. You don't have to set the normal map if you don't have it, so don't worry about that. So I'm going to go ahead, and I think I can just drag and drop this like there. And then I'm going to drag and drop the normal map, and I'm going to hit Add. As you can see, my terrain is now kind of beautiful, kind of small sand dunes in kind of small waves and stuff like that. It looks kind of cool. The second thing is that I want to work with some dunes. I want to add some dunes to it. So I'm going to go ahead and select the, this tool looks pretty good. This is just a brush, and I want to make it really big and quite strong in opacity. And I can now start drawing around in the scene Actually, I'm going to make this less strong. Like, I want to have a little bit of details all over. And then I can go stronger on the surroundings. There we go. And then, of course, since this is a desert, I want to add some sand dunes. Let's see. Let's just add something like this. Looks kind of cool. Actually, I like to draw it this way because it's raycasting into the scene. There we go. I got a huge mountain here, but that's fine. That's fine. It's just a very strong winds in that location. So if I go into this desert now, I can see that this is Origo because I left the sphere in the center. It's just my reference. I like to have this when I start drawing on terrains, just to know where I shouldn't add a mountain and stuff like that. The next thing that desert has, at least to my experience when I was living in the States, was these tumbleweeds. So we need to have a tumbleweed in this desert simulator. And the entire simulation is all about, getting some wind data from some service and then push these tumbleweeds around based on real-world data. So that's what we're currently creating. So the next thing that we're going to need is a 3D model. And like me, when I started, I was the worst 3D modeler ever. I was not able to make anything. I didn't understand how to make this. I didn't understand how to create cool polygons. So I decided to just get my friends to make them for me. But the good thing about Unity is that it comes with an asset store that allows you to get a lot of free models. You can just go to a model you like, and you can search for it, download, and it's automatically added to your project. But since I'm in this audience here, I want to make some free stuff. I'm going to use Paint 3D. Paint 3D is actually a quite simple tool. You can add some cool models. You can create some cool stuff in this. It works like normal Paint, but you have 3 dimensions instead. And it also comes with a 3D library. So I'm just going to use one of those and then import it into Unity. So let's go ahead and search on tumbleweed. There we go. There we have one. So I'm just going to import this. And as you can see, this is a full 3D model, all in Paint 3D. You can even draw on it and add some textures if you want. And then I can go ahead and select Menu, and then save as a 3D model. And Unity understands the 3D FBX format. So this is FBX. So I'm going to go in here and add this to my project, the Desert Sim. I'm going to add, add models. There we go. And then make sure FBX is selected. It can be named Untitled, it's fine. It's an Untitled Tumbleweed. Okay, so I'm going to go back into Unity. The model is automatically being detected. There's a lot of different things that you can do here when you're importing. But I like to, when I export from Paint 3D, I want to use the external materials. What this does, and I hit Apply, what this does is that it takes the textures that got exported from Paint 3D and adds it in a separate folder. So I can see that it's currently in here. So this is a very simple texture. Anyways, I want to drag and drop this tumbleweed into my scene. And I want to add it kind of in the center of the scene as well. It's very small, so let's add some size to it. Yeah, that seems good enough. And as you can see, this is now in origin of my scene, but the problem is that the origin of the 3D model isn't centered. So what I want to do is to actually align these two. So this one is inside the sphere, just make origin kind of the center of his mass. So what I'm going to do is that I'm going to go into this guy, and I'm just going to pull it in there. There we go, and just make it kind of okay-ish. There we go. And then I don't need a sphere anymore. If I go up here, I can drag it there. The next thing I want to do is to add physics to this. Physics is a natural part of Unity. It comes with a strong physics engine. And in order to make something part of the physics engine, I'm going to add a component. Actually, I'm going to do one thing differently here. Instead of affecting the main object, the parent here in scale, I want to just scale the child here instead. So I'm going to revert this back to 1. And then select 2. Let's see, 1. How big is this? OK, I'll just leave it like it was. There we go. Awesome. What I can do now is that I can go ahead and create a rigid body here. So I'm going to add a rigid body. This is a rigid body component. And then I'm going to add it to my scene. And if I go to my camera here now, I can lift it up to the ground a little bit, just so we see it. And if I hit play now, it will be affected by the physics engine, but it will go through the collider of the terrain. The reason for this is that the tumbleweed itself doesn't have a collider. It doesn't have a sphere that surrounds it. So I'm going to go ahead now and add a collider to this rigid body. It comes with a sphere collider. I'm going to add that. It's now going to be super huge. So let's see, radius. There we go. That's good enough. If I now hit play on this guy like that, it's now going to fall down and then start rolling around on the desert. So the next thing I want to do is to add some logic to this that actually hook this up to a socket that provides some weather data from somewhere in the world. But to do this, I actually created in Dolittle a little library that allows me to just add the Dolittle. We're having an open source project, which is based on architecture, but also part of this is to work with Unity. So we created a custom library that I can add to this scene. I'm going to just go into Assets, Import Package, Custom Package, and then I have the Dolittle Unity 3D package here. I'm going to say Open, and this will now just unzip basically all these classes into this. This contains a lot of simulation things as well for vessels and device shadows and stuff like that. It's all built into this. But I'm not going to focus on this in this demo. All I want to do is to add a custom wind zone that I created last week. So let's add a wind zone into this scene. I'm going to right-click, create, and then wind zone. There we go. The wind zone is going to add a couple of components that comes with this Dolittle package. So I want to add rigid body wind zone, and then I'm going to get a weather provider. The weather provider is just a WebSocket that connects to a URL. So I'm going to need the socket address. I have it in my cheat sheet. Let's see. I think this is the guy. And it's actually, for safety reasons, it's actually being connected to this Cisco router over here. That's, again, connected with 4G to the cloud. So if everything works and if everything is correctly set up, this should now, I'm just going to save the scene in case of anything happening. If I now hit play, it's going to fall down, but it's not going to get affected to the wind. Let me just rotate the camera a little bit. Okay, actually, I can move this guy here because he's rolling away too fast. The ground is, it's fine. There we go. You can get stuck over there. If I hit play and I go into this map here, let's see that. Let's say our desert is over here. It's a great desert. You can see the wind direction and the direction of the wind. This will automatically update the socket and apply wind force in that direction on the tumbleweed. And of course, it's not very strong wind, so it might not roll over all the hills because there's some physics involved in the scene as well because of Unity. But it's trying to roll in that direction all the time. So that's a very simple kind of desert simulator. The main reason behind this was to kind of make you all understand how Unity kind of works within the graphics and how you can actually leverage Unity. Not only for creating games, but also for creating some cool stuff. I actually have a friend of mine with me here today. It's Sigbjørn. He's going to help me out with the next couple of demos. But before doing that, I'm going to go back to, let's see if this one was working. Yeah. I'm going to go here first. So as I mentioned, Unity is kind of our primary tool when it comes to rendering in real-time 3D. We could have gone the Unreal Engine direction as well. I'm using that quite a lot in my spare time. But I like to work with Unity mostly because of the availability of assets and 3D models, and just because I've been working with a lot of my private projects, including that space simulator. And then Dolittle is kind of a set of tools that we're working with inside of Dolittle as a company, which is an open source set of tools that allows you to embrace code architecture, it's CQRS, and a lot of event-driven design, and so on. It kind of adds a lot of tools to make that easier for you. And then we also make some interfaces into all of this that makes it easy to use this inside of Unity as well. And by using an event-driven approach in real-time application is very natural because you're constantly rendering stuff. You're working in a loop in 60 times per second or 30 times per second. You can't pull things every now and then. You need to actually wait for something to happen, and it will be triggered. And we kind of spent a little bit of time on trying to create a little bit of different demo for you guys. So we created all this just for you. We're quite stoked to show it, but I want to tell you, there's a lot of risks involved on this one. There's a lot of stuff on stage, so I hope that you can, excuse us if it doesn't really work as we want to. We've been working together as Dolittle with Sigbjørn and Wilhelmsen. We kind of locked ourselves into a couple of offices with Microsoft. They provided us with a room and, Coke and food. And we just went ahead and created a lot of stuff. As you can see, this data here is now kind of tilting. I'm not sure what's happening, but we're going to figure it out, right? Just pretend that this is straight. So anyway, what we have here is actually a 3D model of kind of this. So it's a kind of a twin. It should be reacting to the gyros that maybe have some water on it right now. I don't know. To the gyros, and is trying to kind of orientate everything based on the data that this one sends. So if I go into, I should have a camera here. Let's open this camera. Awesome. So I'm gonna give you a little tour. So in Sandefjord, where Einar Ingebrigtsen, another guy who was working on this, is living, we went to his basement, and he has a 3D printer. So we actually went ahead and 3D printed this little ship. It actually comes with a couple of sections. And inside of this ship, we're having some ballast to make everything kind of even on the water surface. And then we have some batteries. And under here, we have two very powerful engines from an RC boat that a company in Sandefjord gave to us for free, which was kind of cool. We have an ESP device over here. Together with the gyro and so on. And it's currently attached to this aquarium that we also made ourselves. So basically, it was leaking all the way until yesterday afternoon, where we managed to fix everything so it doesn't leak water. So I'm very happy. Hopefully, there's no water on this stage here now. That's good. So what we decided, since this aquarium is very small and we wanted to bring it on stage at NDC, we had to figure out a way to either create a really small ship and radio control it around in this water, or we could think about this differently. And what we decided to do was to attach it to springs. So instead of moving the boat, we moved the ocean around it in kind of a virtual environment. So should we try to see how this works? Actually, before we trigger this off, I think that I want to show you quickly a little bit on the architecture of this. So just bear with me. I'm going to fire this up. So what we have here is, I'm going to go start here. What we have here is kind of a quick architecture overview of how this works. The first thing is that on the vessel itself, we have an ESP32, which is kind of the brain of everything. It gathers the sensor data that's connected to it. We have a controller and so on. Actually, I can show that to you. If I go back to this boat that's currently sinking, you can see that we have two engines in here, and these are all the sensors. We have two engines. We have the controller itself for the motors, and then we have the ESP chip, gyro, and a distance measurer. The distance measurer is something that we just excluded for the demo because it fell in the water. But let's see. But how everything works here is that on the vessel, you can imagine this being on a real vessel. We tried to model all the architecture the way that it actually works in real life. So you can basically apply a lot of the same principles into a real vessel, which is why we're having this super cool Cisco router with us here. You can attach it inside the boat. It's super sturdy. We have a NUC device that kind of works together with all of this to send things up to the cloud. But this is all on the vessel. We have DSP. It's connecting through Wi-Fi currently with this device. And then on, to an MQTT protocol where it's kind of just processing the streams of data and routes this to an adapter inside of a Microsoft IoT Edge. So this is basically an edge device on the ship. And then using this adapter, we now communicate with the cloud. And through the cloud, you go through IoT Hub for deployment and routing, and reaches Kubernetes with Kafka, so to handle all the events. So this is where you kind of process all the events that happens on board. These events are then going to the application itself, which is built on Dolittle, where kind of all the logics is happening. There's a lot of things going on. There's a lot of moving parts. And then through WebSockets, just like I showed you in the desert simulator, we're adding a lot of the interaction layers. One could be a browser. Another one could be a digital twin, like the one that's below us right now. And then lastly, of course, like HoloLens or anything else that you want to kind of interact with your system with. Another thing that we're doing on the edge is to have a machine learning model. And this is the machine learning dude. What we do is that we're having a storage on the vessel itself that kind of always stores the sensor data coming from the source here. And then once we're connected to the cloud, because you're on a vessel, you might not have internet connection, or it might be super expensive, like, you know, $200 per megabyte, kind of expensive, so we don't want to do that as well. So once we're in a kind of a reliable network that doesn't cost a lot, we can go ahead and submit all of this data into the cloud. And in the cloud, it kind of retrains the model constantly. It reads the delta and submits an update back to the vessel itself and updates the machine learning model. The machine learning here is to kind of try to predict the trim settings based on kind of the, what is it called, the, how dirty the hull of the ship is and how it goes through the water and so on. So there's a lot of data points here that's being submitted to the machine learning model. So if we go to, so this is kind of the digital twin 3D model of this. But if we go ahead and enter kind of the dashboard of this, we can see kind of different endpoint. This is getting the same data streams, but we're using it in a very different way. And through this one, we can actually, if everything works, let's hope, we can actually set a position of the ship. So let's put it here. It's very strong winds, and it's, you know, you see the wind direction. It's all actual real weather. Or we can actually go ahead and maybe put it in. Let's see. Let me just. Do I have internet? Yeah. There we go. There we go. Okay, let's see. Are we getting? Yeah, there we go. It was a little bit of delay. So this is in the port just outside of NDC. That's even cooler since we're currently sitting here. And by using this control panel, we created a throttle control that communicates back to the ship that allows us to kind of set the speed of the engine. So I can go ahead and, yeah. Is it connected with the, yeah, let's try that again. Okay, let's try. That's funny. As I said, it was super risky. Do you have lights? Yeah, let's try that again. Let's give it a last try. It's not important. It's just cool. Okay? Let me reload. Okay. It's not working. That's fine. Another thing, let's try the machine learning then. Maybe that's why it was in the syncing mode previously. There's something going wrong here, but let's find out. Let's see if the stream works. Doesn't look like that. Okay. That's fun. Awesome. Okay, what this does was that if you by adding trim to the ship, it's just weights, we would receive under the trim there a warning that saying, hey, the machine learning now detected that the trim is not working. It's suggesting a new trim setting to make your engine more optimum and efficient on the water. Should we do a last try? It was like working when we were setting up. Yeah. Is it both of the engines? Yeah, okay. All right. I think that we just have to move on. The last part I wanted to just mention for you guys is different ways of thinking about software. So traditionally, we're used to, and I'm not saying that this doesn't work. I'm a super fan of how kind of a computer system works, but there's a lot of different ways that you can work around this. Traditionally, we're used at looking at table data in tables. There's a data view. You can see that there's all buttons. There's a button panel. We have images. We have some kind of overviews and graphs and how everything works. We're all used to building software this way. It's very convenient because basically most of the time we're sitting on flat screens. And this is what everyone is having out on their desktop, either at work or out on vessels or anywhere. But if we think about this in a little bit of a different way, I actually took a video from one of the demos that I was working on for the Build keynote in 2016, where we're using Vuforia, which is kind of an augmented reality platform. What you can see here is that we're having a surface device, and we're looking at this marker, which connects a digital world with the real world, so we can start rendering 3D assets in combination with the real world. And as you can see, we're actually having a nice user interface on the side that allows us to have a normal user interface on top of this. We also added ink capabilities, so you can start writing directly on the screen. For example, change, it casts a ray into the digital world and then adds a label with what it detected that was written. This is a shared world, so we communicate this data out to the cloud. And this is another person looking at the same kind of marker from a HoloLens and sees this with a different perspective. Since it's connected, the change label, it was visible on the model. And since it's a digital world, you can start being creative. If I wanted to buy this, maybe I want to see this in real size. I might want to, take it up on stage. I can walk around it. I can see all the details. This is a CAD model. So it was a CAD model that we converted into Polygon to make it as accurate and realistic as possible. It was a couple of millions of polygons rendered inside of this HoloLens device, so it's kind of fun. The other thing that happened in this demo was that the first part, we had this change label. And that was, we added some magic function that allows us to change the different kind of fronts to this caterpillar. So the change here is to kind of modify this into another one that allows you to make this different usage, right? So this is a different way of kind of looking at applications and experiences. And I wanted to kind of end this session with one last thing. If I can get everything working again, of course. Let me just put this on. I always feel like Daft Punk. So let's go into this guy here. And I have to turn this on. It's just in sleep mode, so it should be rather quick. Finding your space. Awesome. All right, you have 3D stuff all over your heads. So if I go into this device portal, I can go ahead and set a live preview of everything I see. Okay, can you guys see this? Okay. This is just a very basic thing that I created last minute, last night after the parties. I decided I wanted to add kind of a little bit of HoloLens to this stuff. But what we did was to take kind of the same vessel model, and I can actually take this guy and I can send it out above your heads into the audience. I hope that you don't mind having a 3D vessel above your heads. And this kind of allows us to look at this stuff from a different perspective, right? So what this is actually doing, but unfortunately the ship didn't work, is to, if it would be connected, it would have this water around it, and then it will be kind of doing the same thing as the digital twin. But I can, of course, scale this to fit the tables I want to have. So let's see if we can hit this. There we go. And I can kind of just make it bigger. I can rotate. You get a picture. There we go. So yeah, if you have the option in a project, or if you have, if you're curious, I would be super happy to talk with you about kind of leveraging kind of different ways of looking at software. I kind of challenge you guys to go and have a lot of fun with this, because once you get started with all this Unity stuff and you start rendering things, you're going to easily get hooked. So let's see, where's my, there we go. So just to sum up this session here, we had kind of a start where we went through kind of what the digital twin is in general, how a living learning module could be a digital asset on your desktop computer anywhere in the world. We also went a little bit of, on how you can make it yourself. I know that it was very basic for you guys who already knows Unity, but hopefully some of you who didn't know Unity, or maybe even haven't tried it before, saw that it's actually not that hard to get started. There's a lot of really good tutorials out there, and it's very easy. It's a free software if you just want to have some fun. So you can go ahead and just download it from unity3d.com, and you start playing around. Then lastly, we went through kind of interaction models and the real digital twin that unfortunately had some communication problem. I'm not sure what happened, but I'm going to figure it out, and we're going to follow up with a cool video of how that works. In addition, we're going to create a very technical walkthrough of how this actually works, because there's a lot of moving parts here, all the way from kind of the Microsoft IoT Edge that's currently stored locally, it's connected up to the cloud, it's sharing data. There's a lot of things going on here. And I think that is actually really cool to take a closer look at. So we're going to create another talk, probably just a web stream or a webcast that we're going to record and publish on our web pages, that we actually go into all the details. It's going to be more cloud heavy than instead of kind of just looking at the 3D and visual part of it. And lastly, of course, we looked at different way of working with software. Today, all this, everything that you've seen has been in 3D. I know that we had 3D in normal desktop applications before, but I also still challenge you on how to kind of leverage the third dimension really smart. A lot of people are just taking 3D and saying, oh, we gotta have 3D because it's cool or it looks nice. But how can you actually use 3D to make everything more natural? Because your surroundings, they're all in 3D, and you might want to start to see, is there a different way that I can actually work with this software? Maybe I can reduce training time because it looks like the real thing, instead of just a huge system with a lot of tabs and buttons that you have to go through a week of training to understand. Maybe you can reduce that time by having a clever software leveraging this third dimension. There's a lot of other cool things, like having a bot that you can chat with. I have a chat channel with my mom on Skype, and then the second channel is with a bot that I can ask the status on a real actual system, and so on. And also, of course, we saw HoloLens today. We saw some augmented reality. We had the Caterpillar demo. But another thing that I want to just quickly mention is the use of VR. You can completely get immersed into a VR scene by using these VR headsets. That's a completely different experience. You can kind of disappear from the real world. So with that, I want to thank you for coming. It's awesome to see this many on a Friday afternoon. So thanks a lot. It gives me a lot of motivation. So I hope that you're going to have a cool last session over there here in NDC. And I'm going to find some food. Thanks a lot.